All right, everybody. Today we want to do a couple of examples centered mostly, not entirely, around power supply. I'm Michel Maharbis.
And I'm Vivek Subramanian. Let's get started. To begin, what I'm going to do is hopefully get you to recall that when we did the phasor analysis, you learned that there is a phase difference between the current and voltage in reactive elements such as inductors and capacitors. Mm-hmm. So now that has an important consequence. You saw that in that last example on phasor analysis that we did in the previous module, which we encourage you to review if you don't remember, that we can use sort of complex impedances to shift individual voltages within a particular circuit.
Okay.
Now what that means is it's possible for us to take circuits that we have, such as this one here, which is a voltage source driving a resistor and capacitor, and cause a phase shift in individual voltages. So now think about what that means for us. We can have an input source with a particular voltage, V in, with a particular phase relationship. And then, depending on where we take our output in the circuit, we could take our output across a resistor, or we could take our output across a capacitor, and we can cause a phase, or for that matter an inductor if we wanted, and we could cause a phase shift either between the V out that we choose to take, for example, V out 2 and V in, or between the various outputs possible, between V out 1 and V out 2.
Okay, what you're saying is that, okay, so you've got this voltage source.
Yep.
It's going to be applied across these two elements. The current will be generated, of course.
Right, and the current is the same throughout.
Okay, and so the value of voltage across the resistor
Yep.
will have, of course, the same frequency as the input source, but the amplitude will change. But even more interestingly, in the case of the resistor, the voltage across the resistor will track with the current going around the loop.
Exactly, because they'll be in phase. The voltage and current will be in phase.
I see, but the current isn't in phase with the Vn.
Not necessarily.
Because there was a capacitor when you're doing the whole
Exactly. In this case, it wouldn't be because of the capacitor. Of course, let me ask you a question, Michel. Let's say I wanted to have a capacitor in there.
Okay.
But I wanted the current to be in phase with the voltage of the source.
Oh, that's sneaky. You're jumping ahead. All right.
How might I do that?
Well, then I basically would want to add an inductor to that capacitor in series so that the inductance and the capacitance, essentially those two impedances cancel each other out.
Exactly. I would pick them such that the 90-degree lag and lead contributed by each one exactly cancel.
Okay.
So they'd have the same magnitudes, and the net result would be the current and voltage would stay in phase.
Okay. I have a suspicion some other interesting things happen if you do that.
Yep.
We'll get to that. But to kind of finish the answer to Vivek's question, in the case of the resistor, remember that this voltage V out 1 is in phase with I, and I is not in phase with V. But in the case of the capacitor, V out 2 is not in phase with I, right? It's off by 90 degrees.
Right.
And so that means not only is there a phase shift between these two things, but there's a phase shift between this C and the Vn. So what you're saying then is that by tuning the values of these things, we can produce output voltages that have known phase shifts, and in the time domain that means time lags, relative to the input.
Right, and we can control those by picking the appropriate values of R and C.
Got it. Okay.
And so these are circuits then that we can use to shift in time the signals that we're dealing with.
Oh, that's right. Because the phase shift, effectively, you're moving the sign over in time.
Correct.
So something will lead or lag with respect to something else. Okay,
right.
That's a pretty general concept. We're not going to do much with it in the rest of this module. We just wanted to really let you know that this is true. This is used a lot. So one place where this is used is if you're building arrays of antennas, and all these antennas are arrayed in some, say, two-dimensional pattern, say n little antennas by n antennas in an array. You might want to have different phase shifts at each of them, and then you can do very interesting things with the radar signal, for example, if they're radar antennas. So these are used in lots of different contexts, and you'll probably come back to them in other courses. Okay, what we really wanted to focus on in this case is a power supply circuit. The reason we want to do that is a power supply circuit, a classical power supply circuit, highlights a lot of little concepts that we can, it's a good time in the course to just really bring them together. Some of them are AC concepts, some of them are concepts in nonlinear devices that we can at least use to begin to introduce you to things like diodes and stuff like that. So what are we going to talk about? We're going to talk about a system that looks like this. We would like to take an AC sinusoidal input, okay, and produce a DC output. Why would we want to do that?
Well, so is this kind of like one of those little power supply things that we plug into the wall, the little bricks, power supply bricks?
Yeah, it's like what your laptop plugs into.
Yeah, got it.
So the wall is putting out AC. We don't want to power our CMOS with an AC input. We want to power our digital circuits with a DC output.
Got it.
DC input for them.
Uh-huh.
And so how do we do that? How do we go from AC to DC?
Well, I think there's various things. One is the AC in the mains, depending on where in the world you live, might be 110 volts, might be 220. That voltage is much higher than the voltage that a typical electronic circuit would need. So first thing, we're probably going to reduce the voltage somehow.
Mm-hmm.
And then we got to go from AC to DC, so we got to find a way to convert it to DC.
That's right.
And then the final thing is, I've heard that a lot of these electronic circuits, they want pretty stable power supplies.
Right.
They don't want the DC to be varying or have any noise on it. So we got to do something to get a nice steady DC signal.
Right, and you've worked it out. So let's give you the steps, and then Vivek will start going through them. The first thing is we're going to make use of something called a transformer. Vivek will talk about that, and that'll allow us to mess with the amplitudes of the sinusoidal signals. So they're going to still be sinusoidal when they're done with the transformer. It's important to remember that. Now, the sinusoidal signal that's been amplitude shifted, essentially, we've just been messed with the amplitude, will then be, in a sense, it's called rectification. We're only going to look at one part of that signal, or we're going to try to capture it also. It's in the positive half plane. So you'll see that it's doing this now.
Wait, so let me look at this. So I've gone from a system that was an alternating current, and alternating means it was partly positive and partly negative, and now I've made it, I guess that's DC, because it's all positive.
It's not really DC. It's time dependent. It's sort of a time.
It's a time variant signal, but at least it's not AC anymore.
It's not a sinusoid.
Right? Yeah.
It's kind of related to one, but it isn't.
Okay.
Now the problem is sort of twofold. One is this is horrible. We're not going to feed this to our circuits. Imagine your DC on your op amp is like going up and down and up and down. So we're going to do an initial attempt by filtering. In other words, by taking something that doesn't like fast changes. And so it'll kind of smooth out fast changes. You can think about it that way.
I can guess as how we might do that.
Okay, well, we will. We'll use it soon.
No, I want to guess now.
All right, guess.
You told me earlier when we were learning about capacitors that capacitors hate sudden changes in voltage.
There you go.
So I can use a capacitor to do that.
That's right. And now, but this is the last part, and Vivek hit the nail on the head. Even this little Ripley thing is not good enough for a really good circuit, and so we're gonna show you a nice way to basically take the little last bit of ripple and kind of smooth it out. Vivek will talk about that because he's an expert, in fact, in some of that stuff. So, all right, you wanna take it away?
Sure. So let's start with a transformer. So we're not actually. Many of you have probably learned about transformers when you took sort of basic electromagnetics in your high school or college physics. So you've probably heard of transformers before, but remember, a transformer is basically two inductors that are placed such that the magnetic fields created by the inductors can interact with each other. Okay, and in fact they're designed so they very closely interact with each other, and the big advantage of transformers is they're very convenient ways to very efficiently convert one AC signal into another. It doesn't change the frequency, but what it does do is it changes the amplitude. And it turns out the relationship between the amplitudes on one of the inductors and the other inductor, which we call the primary and the secondary, is actually given by the number of turns of the coils that form the respective inductors. So for example, let's say I have this particular transformer over here. It has two coils. The primary coil, coil is called coil 1, and the secondary coil is called coil 2. The primary coil has N1 turns and the secondary coil has N2 turns. Well, it turns out there's a relationship between the secondary output voltage and the input primary voltage. V2 over V1 turns out to be exactly equal to N2 over N1. And that has to do with the reasons related to how the magnetic fields interact. But the consequence of that is V2 and V1, that ratio is set by N2 and N1. So, Michel, let's say I wanted to reduce the voltage.
Okay. From like 120,
from 120
to
volts to 12 volts.
Okay, so that's a change of 10x, right?
Yeah.
So I want V2 to be 10 times lower than V1,
yep.
Right? So then I want N2 over N1 to be 10 times lower, essentially. So I want 1 over 10. So does that mean I get, like, say, maybe 100 turns on N1 and 10 turns on N2?
Exactly right.
Okay.
Now, it turns out, remember that assuming that these were ideal inductors, there's no resistive loss in these, right? So one of the important consequences of that is, first, these are very, very efficient. Okay, they can be extremely efficient, but because there's essentially no place for power to be burnt off as heat, there is essentially just as we have a step down in the driving voltage, okay, there'll be a step up in the driving current.
Oh, because P goes IV, right?
Right.
And you can't have the P in better be the P out
Exactly.
if you're not burning it away.
So that's right, but that makes it very good, right? Because basically what happens is if I have a load here that is designed to run at 12 volts but draws 1 amp, the current that we draw from the 120 volt source will be 0.1 amp.
Oh,
Makes
that
sense?
makes sense. That makes sense.
So that's
Okay.
kind of nice. That's why these are great. They're very, very efficient.
So you can get current or voltage amplification effectively. if you want,
Exactly.
at the expense of the other. Of
That's
the other
right.
factor.
That's right.
Okay, fair enough.
Okay, so we've covered the first block. Maybe Michelle, you can now talk about going from AC to that sort of bumpy DC type thing.
Okay, and to be clear, basically we would use this to go from 120 to, say, whatever, 10 volts, but it would still be sinusoidal.
Exactly.
Okay. All right. So here's something called the half-wave rectifier. This is a pretty old circuit, and it's based on a device that you may or may not have seen previously. So we're going to make it sort of very simple for you in this example. This device is called a diode. Okay? And what we're going to do is we're going to feed it an input. And remember, our input is the sinusoidal signal coming off the transformer. So it's still an AC sinusoid with an amplitude of some kind. And you'll notice that there's a resistor, a diode, and then there's a resistor here, and the voltage across that resistor is essentially going to be V out. That's what's going to go on to the next stage. Now, you can think of a diode like a check valve. A check valve is what's on your bicycle tire. If flow wants to go one way, it can, but if current wants to go back the other way, it can't.
I get it. So it essentially allows current, in this case, left to right, but does not allow right to left.
Right.
Got it.
So what that means is when the current is the voltage is positive and thus the current is positive because there's a resistor here, you're going to basically have, right, because you can just do KVL around, this positive voltage will give you a current going like this, going left to right. So positive voltage will give you positive current. That current will be fine with one
Okay.
little wrinkle. But then when we get to here, wants to go the other way, it won't. It'll zero out. It's just like your bicycle.
I got it. So the idea is because it blocks current going right to left, it effectively isolates the voltage source from the rest of the circuit. It looks like it's at 0 volts when it's in the negative
Right.
half cycle over here.
And there's one other little wrinkle, and that you can learn why that is in your semiconductor physics courses. But the other wrinkle is the internal, the way that the internal physics of this work out. This enforces a tiny little voltage drop across it. It just does. And so in other words, the waveform you'll get actually won't track the blue one exactly. It'll be the blue one minus about 0.7 volts for a typical one of these diodes, these silicon diodes. So you see the red line is actually what you get. It's a little lower than the blue line, but it follows it exactly, and then it hits 0 and just flattens out until the next time the sinusoid comes back up positive.
Okay, that's great. So this looks kind of like a way to go from AC to DC, but it sure seems like I'm wasting a heck of a lot of power because I'm basically throwing away that whole negative half cycle that I had there.
Right, so this part of it, you'd be wasting that power. Thankfully, long ago, when people with long beards and pipes thought about this problem, they came up with a solution.
That's right, and the solution was the full wave rectifier. So remember, the key point of the full wave rectifier is voltage is relative, right?
Okay.
And if voltage is relative, all we need to do is make sure that we sort of route the voltage around such that we always have a positive going to one side of our DC circuit requirement and a negative going to the other. And I'm going to explain to you what that means. Okay, so let's say that we have our same rectifier, so we're driving it with this AC source, but now I've got 4 diodes forming my rectifier, and my load sits between them in this way. Okay,
So the load resistor is the same, but now we've got 4 diodes instead of 1. And you
exactly.
kind of set them up all
I've
weird.
set them up in a particular way, but I'm going to walk through how this works, okay? So let's say I'm in the positive half cycle. Look at how I've wired the diodes. So on any particular connection to the source, there'll be one diode connected to it that's facing out and one diode connected to it that's facing in.
Oh,
Okay.
so one diode that will let current go in one direction but not the other for whatever direction.
Exactly. All right, so now watch what happens. Let's say I'm in the positive half cycle. Well, in the positive half cycle, which diode do you think, of these 2 diodes, let's call it the top left and the top right, which diode do you think is going to be on, Michelle?
Well, remember from the last diagram, the sort of check valve behavior, it's from the back of the triangle, sort
right,
of
it
into the triangle.
follows the arrowhead.
Follows the arrow, exactly. So that means that the positive current will want to follow the right diode, but it'll hit a roadblock on the left one.
Exactly.
So that'll be off. And then it comes around. Now the bottom diode on the right side is also a roadblock, so it's
so
open essentially. So it's got to go.
So it cannot come down this way.
Right. Got to go through the resistor.
Right. Now
and
what happens
then
here?
it's going to go down through this other one and back through the source. Back to the source.
Now, it comes down through this one. It could also walk up through here, but it won't because this is already at the high voltage. It wants to get to the low voltage.
Oh, that's right. That's a good wrinkle to point out.
So it's going to come back down again, and now think about what happens. So other than that small voltage drop that Michelle told you about, in the positive half cycle, I am able to deliver current to the load.
And I get 2 drops now. I must have 2
That's right.
voltage
I have 2 voltage drops because I'm coming through this the top right diode and the bottom left diode.
Okay, it works. Now what about the other side?
All right, so let's look at the other half cycle, okay? Now I'm going to look at the negative half cycle. Well, in the negative half cycle, okay, I get current flowing down through here because it's now flipped, right?
That's the positive current.
This becomes the positive current. So it comes through the bottom right diode, as we spoke about before, still comes through the load, and still now comes up through this top left diode. Now, here's a key point. What direction was the current flowing in the resistor in my
that's the whole trick. So the current's always flowing from right to left.
Exactly. In the resistor, current is always flowing from right to left. So it's right to left over here in the top half cycle, and it is right to left over here in the bottom half cycle. So as far as the resistor is concerned,
It never flipped.
It never flipped. And the reason that works is the voltage across the resistor is all relative. So as far as the load is concerned,
Right.
it's seeing both half cycles. It's not throwing any away. So we call this a full wave bridge rectifier. And we call it a full wave bridge rectifier because of 2 things. One, full wave because it keeps both halves. And we call it a bridge rectifier because of this particular arrangement where we set up these 4 diodes in the
just like a Wheatstone bridge with a bridge of 4 resistors.
Right. Okay?
Cool.
So now the benefit of this over the half wave is it's much more efficient because we didn't throw away that other half cycle. The disadvantage is it takes more diodes, there's 4 instead of 2, and we have to account for the 2 voltage drops as opposed to the 1. And that's why you see that the voltage that we get is shifted by 2 voltage drops rather than by 1.
Pretty cool. All right, so now we've got it so we've got these little wrinkles. So we've got the output of the last stage is this sort of constant little half parts.
So it's the dashed black line.
The dashed black line, that's right, as a function of time. So now what we're going to do is we're going to run this across a circuit that has a parallel resistor, in parallel with a capacitor and measure the voltage here. Okay, so think about this. Think about everything to the left of this point as, you can almost think about it as a source, a voltage source that produces this dashed line input.
So this bumpy
thing.
half sinusoid.
Okay, so now the capacitor doesn't like changing as fast as this for the appropriate size capacitor. We'd have to pick a right one, right?
So that'll probably be a pretty big capacitor.
Exactly. And so remember, capacitors don't like these very fast changes in voltage. That's one way to think about this. So what happens is, the other way to look at it is this is just an RC circuit. And the RC has a certain discharge time. So let's look at it. So here, let's start at this point. All right, my signal comes up. Okay,
I charge up the capacitor.
Charge up the cap. Now at this point, my signal wants to go down, and this cap is going to start discharging. But it can't discharge as fast as the drop because you've picked the RC time constant of this so that it's much longer.
Okay, I get it. And now it's kind of interesting because it's never able to discharge back this way because these diodes block it because they're in the wrong direction.
Mm-hmm.
So it's only able to discharge through my load.
That's right.
Okay,
that's right.
Makes sense.
So and you can think of this as injecting current into this RC.
Right. So it charges the cap through those diodes.
Right. This current we were talking about goes through, charges the cap. The cap wants to discharge, but it can't because we've picked this RC such that the tau is much longer than this.
Okay, so now let me guess. The more smoothing we want, in other words, it's going to drop off slowly, but if we want it to drop off as little as possible, we'd usually pick a really big C, because that'll give us a lot of charge in that capacitor, which means it'll discharge very slowly.
That's exactly right. And so the bigger the C, you might even be able to, this is a little exaggerated for a realistic one, you might come down and just barely discharge, and then of course the thing flips again and it starts to charge it up just a little bit and discharge. So there's a lot of charge always on this cap.
So in real power supplies, you'll often find that the value of that cap that's used for filtering is several thousand microfarads. So in the millifarad range is certainly common.
That makes sense. Now we're going to come back to this, by the way, this exact circuit afterward, and we're going to teach you how this is actually a filter in the formal sense. And we'll show you how, once you recognize that this is a filter in the formal sense, this waveform would have been filtered to look like this. But in the time domain explanation, it works just as well. In other words, this thing can't discharge as fast as this wants to, so it just sort of coasts along. Okay?
Okay, makes sense.
All right, so now we've got a ripple. So that's not great. We really want a steady 10 or 12 volts for our power supply. So how the heck are we going to get rid of this ripple?
Well, that's pretty easy. Here's what we do. Here's what I'm going to suggest. I'm going to suggest that we have this ripple. If we pick the capacitors and resistors properly, it's pretty small. What if I just use some sort of cutoff circuit that just says, well, I'm going to reject everything above this point?
Oh, so you're saying that it's small enough that last little bit of rejection, it's an inefficiency, but not a very
Yeah, I mean, I'll burn this as heat. But if I have something that just sort of burns off any excess over here, it's going to be heat. But if I've got this relatively smooth, I'm not losing too much.
Right. And we should say that this is a really exaggerated drawing.
Exactly.
They never look this crazy.
Right. This would be a really poorly designed system if it was this much.
Okay.
Anyway, so we actually use something that does exactly that. What we do is after that filter, we put in something called a Zener diode.
Oh, so here you reproduce the whole circuit, actually.
Right. I put it all together.
The whole thing together. Okay. Sorry.
Okay? So I put the Zener diode here. And what the Zener diode does is it's exactly what I said. It's basically a cutoff. Think of it for the purposes of this class as a cutoff circuit. It will burn any extra, any voltage, any electrons, any power associated with voltages above the cutoff of this Zener diode will get shunted out and burnt off as heat. Okay? And it'll ensure that the voltage across the Zener diode is held at a particular voltage, and that's specified by the manufacturer for the Zener diode.
So you still need the rest of the circuit to get it up to that minimum point, but every time it goes a little bit higher in terms of those ripples, this thing just drains it down.
Exactly.
Keeping it totally flat.
Yeah, so you need that filter, because if you didn't have that filter, anything below the Zener diode cutoff would propagate through. The Zener diode only cuts off above a particular voltage.
Got it.
So you need the filter and all to take care of that, but provided you've designed your filter properly, you can get rid of the ripple by ensuring that your Zener diode cutoff is below the ripple level. And that'll give you a really, really stable voltage. And this works. This is sort of one of the easiest, reasonably well-regulated power supplies that you can build. It's not what's typically used in more efficient systems, because you have to deal with the heat loss from here, and it turns out Zener diode voltage control is not great, and it turns out to be dependent on the load. So, but this is a workable system, and you could build one and it would work reasonably well.
So the Zener diode is the simplest form of a voltage regulator.
Exactly.
But they're of course more complicated. Okay.
Correct.
Well, I think we'll stop here. We hope you enjoyed this little power supply digression, and we'll come back pretty soon and move on with other modules.
Sounds good. See you then.
See ya.